very good morning to Dr. Ramani and my beloved friends. We are from Group 4. My name is Sheng. Together with Benjo, Yusuf, Afiqah and Najaa, we will be presenting on the topic competitive learning and coherent self-organizing network. In competitive learning, the keyword is neurons compete with each other. The objective of the neural network is to perform unsupervised clustering and pattern recognition. Referring to the figure on the left, we have a two-layer neural network, input and output. The special about this network is the output neurons are interconnected. This is because in competitive learning, we wanted to compare which output has the highest score. Only the winner neurons gets to update its weight. Therefore, we can also say that competitive learning uses winner-take-all learning rule. I'm going to explain the simplified algorithm of competitive learning. To initialize the algorithm, we need to ensure that all the weights are normalized in such that the sum of square of the weights are equals to 1. Upon initialize a normalized weight, we should see that now we have a common starting point for all the outputs. Moving on, we will calculate the output of each neurons. Remember, only the output with high score gets activated, while the weights connected to other neurons remain constant. Choosing the suitable update rules is an art by itself. According to the standard update rules for competitive learning, the new weights can be found as below by calculating the learning rate times the input minus the weights. Now, all you need to do is repeat step 2 and step 3 until you reach either convergence or specified steps. Please note that competitive neural network does not guarantee convergence nor number of correct clusters. Just look at the example on the left. Although we have specified 8 clusters as our parameters, cluster 1 and cluster 2 overlap with each other, resulting on effectively only 7 clusters on the map.
For our competitive learning case study, today we're going to be analyzing an improved version of the competitive learning neural network for network intrusion and fraud detection. So network intrusion and fraud detection are extremely critical to e-commerce businesses. And as e-commerce has continued to grow in North America, more than 20% every year, fraud continues to cost e-commerce businesses an alarming amount of money. Based on a survey results done in 2009, on average, 1.6% of orders turned out to be fraudulent, which eventually cost $3.3 billion. Don't mind me, I'm sipping my tea. Now back to our competitive learning case study. Network intrusions, on the other hand, attack e-commerce companies from the back end, causing downtime of web servers, leaks of private business information, and leaks of confidential customer information. This eventually damages the customer's confidence in their credit card providers. So, now that this has been established, it is the intent of e-commerce companies and credit card providers to prevent and detect fraud as soon as possible. So this study proposes 2 new clustering algorithms, an improved competitive learning neural network and a supervised improved competitive learning neural network for fraud detection and network intrusion. Now, to give a background on the competitive learning models we employ, the improved competitive learning network is an unsupervised clustering algorithm that, in addition to the winner-takes-all rule, there is now a reward punishment update rule, and this update rule helps to overcome instability and accelerate the training process. Secondly, we have the supervised improved competitive learning network, which uses data labels to guide the training process to achieve a more accurate clustering. So when we take a look at the left and we compare the 2 data sets we have there, the one on top is an unsupervised data set. It is unlabeled. But comparing that to the bottom is labeled and more accurately clustered. So the supervised improved competitive learning network can be applied to both labeled and unlabeled data, and it is independent from the initial number of clusters. Referring to the data sets again, we can see that the circles, the clusters, are no longer in the same positions they were when we compare the unsupervised clusters and the supervised clusters. Now, for the improved competitive learning network, I mentioned that an additional rule was included, the reward punishment rule. But what does that really mean? What it means is that we understand that in a traditional competitive learning network, we have a winner takes all rule where only one neuron is affected by the output of the neural network. But now, all the neurons are affected by the output of the neural network. Although we only have one winner, but now we have multiple losers. So when we have a cluster of data points and all the neurons compete with each other, the neuron that wins moves closest to the data points, while all the other neurons are now losers and they move further away from the data points. This helps to accelerate the training process and overcome instability. Now, in the case of the supervised improved competitive learning network, I should mention that this is built on top of the improved competitive learning network, which means that it also has the reward punishment system. But now we have labels in our data sets, and the new rule is that only neurons in the same class have the right to compete to win. So this helps to minimize the impurity among groups, where in each cluster we have some data that has been identified as fraudulent and other that is unfraudulent. But now, because clusters only compete depending on their classes, we can have a more accurate and a cleaner data set. So it helps to minimize the impurity in our data sets and also reduce the number of groups. Now, onto the results of this experiment. So the data used in this experiment are a portion of credit card payments from Vesta. Vesta is an e-commerce transaction company, and the data contains 3 months of over 200,000 credit card transactions, in which 200,004 of them are normal, and then about 2,500 are fraudulent. So we can already see that the number of fraudulent transactions is just a portion of the total transactions made. But our goal is to detect fraudulent transactions. And in fraudulent transaction detection, recall rate is more important than overall accuracy and precision because we want our neural network to be able to identify fraudulent transactions when it comes across them in the clusters. So, for the supervised improved competitive learning network, our recall rate is 79.1%, which is more than 20% higher than the traditional approaches like the k-means clustering or the standard competitive learning network. So, it shows an excellent performance in solving classification problems using clustering approach. Thank you.
Hello, my name is Benjo Mabila Jack, and I'm going to take you through the Kohonen self-learning, also known as self-organizing map. The algorithm is inspired by the organization and functioning of the human brain's visual context. The main idea behind the Kohonen self-learning is to create a low-dimensional grid or map of the neurons. During the learning process, the algorithm adjusts the weights associated with each neuron based on the input patterns. The objective is to place the similar input patterns close to each other on the map, thereby creating arrangement presentation of the input data. Okay, in this slide, I'm going to talk about self-organizing map algorithm. From my left hand side, you see we have a graph, and this graph we have two neurons and the six inputs. So the red one are the inputs and the two squares are the neurons. The first step is to select the random input and then compute the winner neuron. What is a winner neuron? Is the neuron closest to the input. For example, if we had selected this one, the input from the y-axis, that means that our winner neuron is going to be the green square. Okay, let's see from the next slide. The third step is to update the neurons, which means that the neuron is going to be similar to the input. In the previous slides, I give example of selecting an input from y-axis. If you see from this slide in the graph, you see that the green neurons has moved a little bit close to the inputs of the y-axis. This means that when we selected the winner neurons, it moves toward the selected inputs, and our selected inputs was this one. I mean, it was the input from the y-axis. So you see, it has been displaced toward the selected input. The fourth step is to repeat for all the input data. Repeat the process for all the input data by selecting different input. Here we have selected a different input from x-axis, and that's why you have seen our neuron has moved toward the x-axis. The final step is classification of input data. The input data that are closer to the green neuron will be classified as green group, and the input data closer to the blue will then be classified as blue group. This is all from me. Thank you.
The case study chosen for Kohonen self-learning is the neural network analysis of social medical data to identify predictors of undiagnosed hepatitis C virus infection in Germany. So the background of this case study is the chronic hepatitis C virus, or also known as HCV, is slowly debilitating and potentially fatal disease with a very high estimated number of undiagnosed cases. The detection of unreported infection is actually very crucial to eliminate hepatitis C on a population basis. Thus, Germany Liver Foundation obtained data from two German healthcare insurance companies on large group of patients with proven hepatitis C virus to identify predictors for undiagnosed HCV infection through in-depth artificial neural network analysis. Moving on to the next part, which is the method. The Kohonen artificial neural network is used to analyze social medical data of 1.8 insurance for predictors of undiagnosed HCV infection. The network was trained from a subgroup of 2,544 patients with confirmed hepatitis C virus infection, excluding variables directly linked to the diagnosis of HCV. The training results were then visualized in 3D, and the distribution and characteristics of the cluster were explored within the map. Next is the result of the case study. The current figure shows the Kohonen self-organizing map generated through 20 different epochs. From the figure, all 2,544 patients with confirmed chronic HCV diagnosis were localized in a clearly defined cluster. An additional 2,270 patients who had not been diagnosed with hepatitis C was also co-localized to the same cluster. This figure indicates there are social medical similarities and a potential elevated risk of infection between those different groups. To conclude, this artificial neural network approach may allow for a more efficient risk-adapted HCV screening. However, further validation of the prediction model is required. That's all from me. Thank you.
Welcome to the last part of the presentation. To put it simply, the objective of the Kohonen network is to identify and organize the similarities within the input dataset. It creates grid-like structure which allow visualization in a lower dimensional grid or space for its topological representation. Kohonen network is especially useful for data visualization and analysis as well as pattern recognition tasks. To conclude, there is a relationship between Kohonen Organizing Network and Competitive Learning Network. Kohonen is a subset of competitive learning which belong to unsupervised learning technique. That's all from our group. Thank you.